In this lecture, we're going to introduce the concept of the exchange interaction. And we're going to use it to demonstrate that it's lower energy for two electrons that are interacting via their Coulomb interaction to have their spins parallel than to have their spins anti-parallel, all other factors being equal. So the energy of two electrons with parallel spins is lower than the energy of two electrons with anti-parallel spins. And this difference in energy we call the exchange energy. This is important, of course, for the magnetic properties of a material, because an electron has a magnetic moment associated with its spin. And so the case where two spins are parallel to each other has an overall magnetic moment. Whereas when the two spins are anti-parallel, the total magnetic moment is zero because the magnetic moments of the individual electrons point in opposite directions. Okay, and we're going to use as our example material, again, the simplest possible material we could think of, to demonstrate this, the excited state, the first excited state of the helium atom. And we're choosing the first excited state because we want to have the possibility of comparing the energies of the electrons parallel to each other and anti-parallel to each other. So we're going to look at the energy difference between the scenario where an electron in the 1s orbital and an electron in the 2s orbital have the same spin orientation. And we're going to compare that to the case where the electron in the 1s orbital and the electron in the 2s orbital have opposite orientations, and work out which is the lowest energy. If we look just at the ground state of the helium atom, where both the electrons are in the 1s orbital, then it's not possible for them to have their spins parallel, and so we can't make the comparison. So let's start by writing out the Hamiltonian for these two electrons. And we'll decompose our Hamiltonian into a term which we'll call H1, and this represents the Hamiltonian for electron 1, for one of the electrons, if it were the only electron there. So this consists of two parts. It consists of the kinetic energy for electron 1. So we'll label its kinetic energy with a 1 to indicate electron 1, plus the potential energy for electron 1, if it were the only electron there. And so the potential energy is just the Coulomb interaction between electron 1 and the nucleus. So R1 here is the distance of electron 1 from the nucleus. And then the second term, which we'll call H2, has exactly the same form, but It's the kinetic energy plus the potential energy for electron 2. So we'll write the kinetic energy with the label 2 to indicate electron 2, and then its potential energy from its Coulomb interaction with the nucleus. And if the electrons were non-interacting, this would be the entire Hamiltonian, and the energy would just be the sum of the energy for electron 1 plus the energy for electron 2. But because our electrons are interacting, they experience a Coulomb interaction between themselves. There's a third term in the Hamiltonian, which we'll call H12, to indicate that this is describing both electron 1 and electron 2. And this is the Coulomb interaction between the two electrons. And it's positive because both the electrons have the same charge, and so it's repulsive. And R12 here is the distance between electron 1 and electron 2. So this is our Hamiltonian, and we want to calculate the energy. Which we'll do in our usual way of taking the expectation value of the electronic wave function with this Hamiltonian. And this time, our electronic wave function is a function of the positions of both the electrons. It's a 2-electron wave function. It's a many-body wave function describing both the electrons. So it's a function of both the position of electron 1 and the position of electron 2. So we want to calculate this energy for both cases. The case where the spins are parallel and the cases where the spins are anti-parallel. Okay, so that's the problem. How will we proceed? Well, we have to first write down these wave functions for the case where the spins are parallel and where the spins are anti-parallel. And so we're going to do that. We're going to write down correct wave functions, but the derivation will be a little bit qualitative. So first of all, let's remind ourselves of the Pauli principle. Which we're going to write in perhaps a more rigorous form than you've seen before. We're used to the Powly Principle telling us that any atomic orbital or molecular orbital can take only 2 electrons, which have to have their spins anti-parallel. A more rigorous way of stating the Powly Principle is that the total electronic wave function must be antisymmetric with respect to the interchange of any 2 electrons. In our case, we only have 2 electrons. So when we swap those 2 electrons, our wave function has to change sign. It has to not change anything else. It has to only change its sign. And our wave function is a product of the spatial part, the part that depends on the positions of electrons 1 and 2, and the spin part, the part which depends on the orientation of the spins. And so we have two options or two ways that we can write down a wave function for two electrons that satisfies this Pauli principle. We can have the spin part be symmetric, in which case, in order to have the total wave function be antisymmetric, we have an antisymmetric spatial part. Or the opposite scenario, we can have an antisymmetric spin part and a symmetric spatial part. And a symmetric spin part, what it means if the spin part of the wave function is symmetric, is when I exchange the two electrons, I exchange their spins, then the wave function remains unchanged. And that's the case when I have both of my spins parallel. If I now then swap the spins, my wave function doesn't change. On the other hand, if one of my electron spins is opposite to the other, if it's the negative of the first spin, then when I exchange my two spins, I get minus the spin part of the wave function. So these two spatial parts of the wave function, these two distributions of the two electrons, correspond to the two different arrangements of the spins that we want to explore. Okay, so now let's write down spatial wave functions that have the required symmetric or antisymmetric form that we can then use to calculate the total energy. So we make a table of the spin part of the wave function as being symmetric, so the spins are parallel. Then the spatial part of the wave function has to be antisymmetric. And the way that we can make an antisymmetric wave function of electrons 1 and electron 2 is to put electron 1 in the 1s orbital, electron 2 in the 2s orbital. Of course, we can equally likely have electron 1 in the 2s orbital and electron 2 in the 1s orbital. And if we want our wave function to be antisymmetric, we have to have a minus sign here, such that if I exchange electron 1 with electron 2, my wave function as a whole changes sign. I would then end up with plus electron 1 in the 2s, electron 2 in the 1s, minus electron 1 in the 1s, electron 2 in the 2s. And just to be neat and keep the normalization, we'll put in a 1 over root 2 here. So this is a little bit hand-wavingly. One can actually show rigorously that this is an appropriate spatial part of the wave function, but in this case. Then let's look at, and this is the antisymmetric spatial part. Now let's look at the antisymmetric spin part, and we'll write down now a symmetric spatial part of the same form, electron 1 in the 1s orbital, electron 2 in the 2s orbital. But now we'll combine the exchanged combination where electron 1 is in the 2s orbital and electron 2 is in the 1s orbital, but with plus sign. So now if I swap electron 1 with electron 2, this wave function remains unchanged. It's symmetric with respect to the exchange of electron 1 and electron 2. Okay, so given that we have to a little bit accept on faith that these are two appropriate wave functions, spatial wave functions, to describe the two electrons in the excited state of helium for these two spin scenarios. But given that we have now these spatial wave functions, we can work out the energies in the two cases. And this one I wrote out for us already because it's a bit complicated and I would probably make a mistake. And so let's talk through this and see what it means. So this is now the energy, which is the expectation value of the wave function, which is a function of electron 1 and electron 2, with the Hamiltonian that we wrote down before. And the Hamiltonian, remember, was H1 plus H2 plus H12. And the Hamiltonian H1 only operates on wave functions of electron 1. The Hamiltonian H2 only operates on wave functions of electron 2. And H12 operates on both parts of both electron 1 and electron 2. Okay, so to go from the first line to the second line, all we've done is substituted the form of the wave functions that we just wrote down, electron 1 in the 1s orbital, electron 2 in the 2s orbital, plus for the symmetric case, or minus for the antisymmetric case of the spatial wave function, electron 1 in the 2s orbital, electron 2 in the 1s orbital. And here's our Hamiltonian, and then here's the wave function again. And so now we're going to work out all of these terms. So the first term, we have electron 1 in the 1s orbital times H1 times electron 1 in the 1s orbital. And the electron 2 term doesn't contribute here because H1 is only operating on electron 1. And then we have a term with electron 1 in the 2s orbital times H1 times electron 1 in the 2s orbital. And this part is just the energy of electron 1 in the 1s orbital plus the energy of electron 1 in the 2s orbital. So we'll call this just E1. The second row is of the same form, but now it's for electron 2. You see in the first row we had only electron 1, in the second row we have only electron 2, and the first term is the energy for electron 2 in the 1s orbital. The Hamiltonian here is only the Hamiltonian for electron 2, and the second term is the energy for electron 2 in the 2s orbital. Again, we have only the Hamiltonian for electron 2 here. So let's call this term E2. It's just representing the energy for electron 2. And of course, it's going to be the same as the energy for electron 1 because the two electrons are indistinguishable. Let's have a look at the next term. So in the next term, we have on the left-hand side electron 1 in the 1s orbital and electron 2 in the 2s orbital. Then we have the Coulomb interaction operator. Then we have again electron 1 in the 1s orbital and electron 2 in the 2s orbital. And likewise, the fourth line, we have electron 1 in the 2s orbital, electron 2 in the 1s orbital, and then on the right-hand side, we have again electron 1 in the 2s orbital and electron 2 in the 1s orbital. So we'll look in the next slide at exactly what these mean, but for now let's just call these terms K. And the last, and to note so far, all of the signs have been the same. There's been no difference whether we had a plus or a minus in the form of the wave function. That changes in the last terms. The last terms are positive when we had the symmetric spatial form of the wave function, and negative for the antisymmetric spatial form of the wave function, and these are going to change the sign of these are going to change the relative energies of the two wave functions. So let's have a look at these last terms here. We have electron 1 in the 1s orbital, electron 2 in the 2s orbital, the Coulomb interaction between them. Then on the right-hand side, it's a little different now. Now we have electron 1 in the 2s orbital and electron 2 in the 1s orbital. And so we've exchanged between the left and the right, we've exchanged the orbital that each electron is sitting in. And likewise in the bottom, but we have the other way around, electron 1 in the 2s on the left and electron 1 in the 1s on the right. So we'll call these terms, this is not just our choice, they're generally called J. And so we see that our energy of the two wave functions is E1 plus E2 plus K plus or minus J. Well, remember the plus is for the symmetric spatial part. And so anti-parallel spins, and the minus is for the antisymmetric spatial part. And so parallel spins. Okay, so let's have a look then at what each of these terms mean. So E1, we already mentioned, is just the expectation value for electron 1 in the 1s orbital, which is equal to the expectation value for electron 2 in the 1s orbital. And E2 is the expectation value for electron 1 in the 2s orbital, which is equal to the expectation value for electron 2 in the 2s orbital. So these are just the energies of the non-interacting electrons and of course the energy is the same whether it's electron 1 in the 1s orbital or electron 2 in the 1s orbital. E2 is the energy of electron 1 in the 2s orbital or the energy of electron 2 in the 2s orbital. So that's straightforward. Let's look next at the K integral, which is a little bit more, a little bit less intuitive, I'd say. So the K integral, let's write it out again and rearrange things a little bit. We have the 1s orbital on the left-hand side here, which of course is the complex conjugate of phi 1s of R1. And on the right-hand side, we have phi 1s of R1 again, and it's in this case real. And I'm just going to group those together. Then we have our H12, which is E squared over 4 pi epsilon 0 times the distance between electrons 1 and 2. And then we have our electron 2 in the 2s orbital. And again, I'm going to group these together, the complex conjugate part and the real part, integrated over all space. And if I think about what this complex conjugate times real part means, I can write it as the square modulus of the electronic wave function squared which is just equal to the charge density of electron 1 in the 1s orbital. And on the right-hand side, I have the charge density of electron 2 in the 2s orbital. And I integrate over all space. So I have the charge of electron 1 in the 1s orbital interacting via the Coulomb interaction with the charge of electron 2 in the 2s orbital. And so I can see that this is just the Coulomb interaction between the two electrons. Electron 1 in the 1s orbital and electron 2 in the 2s orbital. And the second term is exactly the same, but it's written for electron 1 in the 2s orbital and electron 2 in the 1s orbital. So these terms K are the quantum mechanical exact analog to the classical Coulomb interaction between two charges. So what about the last term, J? So in the J term, I have electron 1 in the 1s orbital on the left and electron 2 in the 2s orbital. So at the moment it's looking like the Coulomb interaction term. They're interacting via the Coulomb interaction. But on the right-hand side, I have electron 1 in the 2s orbital and electron 2 in the 1s orbital. So I can't rewrite it in this form of a charge density of electron 1 in the 1s orbital, because on the left, electron 1 is in the 1s orbital, but on the right, electron 1 is in the 2s orbital. And likewise, the bottom line, I start with electron 1 in the 2s orbital on the left, but on the right, electron 1 is in the 1s orbital. The interaction is still the Coulomb interaction between the electrons, but they've been exchanged. The orbital that they are occupying has been exchanged, or if you like, the electrons have been exchanged between the two orbitals. And this term has no classical analog. We call this the exchange interaction. And I really can't give you a kind of better analogy of what this means, because there is no classical counterpart. It's a purely quantum mechanical interaction. So we can say that the energy of the symmetric spatial wave function, which corresponds to having anti-parallel spins, is higher by an amount 2j than that of the antisymmetric wave function, which corresponds to the parallel spins. And so the magnetic arrangement, the arrangement with the spins parallel, which has a net magnetic moment, is the lower energy arrangement. Remember, though, that the ground state of helium is not magnetic. So if we order our energies in terms of their energy, then the lowest energy, we order our spin arrangements, then of course the lowest energy overall, the ground state of helium, will have both of the electrons in the 1s orbital. The highest energy of the states we've considered has one electron in the 1s and one electron in the 2s that's anti-parallel, and in between we have one electron in the 1s and one electron in the 2s with the states parallel. And the difference between these two is 2J. So we can see that for helium to be magnetic, we would need for this energy difference, the energy difference of taking an electron from the 1s to the 2s, to be less than the energy that's saved, the 2J that's saved by giving both of the electrons the same spin, and that's not the case.